So far we've been taking a look at lateral magnification. If you think about it, that's usually not the most useful definition of magnification that we could have. For instance, just go stick your thumb out at different distances in front of your eye. And you'll notice that if you put your thumb farther away from your eye, it seems smaller. But of course, your thumb is the same height the whole time. So it's only part of the story if we say that, hey, the system gives us a lateral magnification of 10 power. But if it parks that image way out in outer Bundinavia somewhere, then it might take up less angle in your eye. And that wouldn't be terribly useful. So the usual standard that we use for defining angular magnification is to say, well, how big could you possibly ever see something? And that would be if you stick it out at your near point. So this distance is about 25 centimeters. When you look at it, it's going to subtend some angle, we'll say theta near point. Now, if you instead go and look at it through some magnifier, we can go ahead and see what angle the image you make subtends. It may be that the image is, so if this is the image of what you're looking at, after you've looked at the object, say, here's my object, through the lens, you go and look at it and say, hey, that's a much bigger angle now, theta. So we define the angular magnification of a simple magnifier here to be the angle that you get the image to subtend over the best you could do if you just plain held the thing up to the near point of your eye. So with a simple magnifier, like Sherlock Holmes's magnifying glass, oops, there we go. If we go and stick a lens in the way, usually what you'll do is, as we've learned from looking at case 3 situations, is you'll want a converging lens, and you'll want to stick the object just inside the focal point. So by doing that, you know that you're going to make some sort of absolutely enormous image. If we go and track the central ray, somewhere back over, say, here somewhere. That's not what's really important. What matters is the angle that we're taking up, and it's this. So this is our angle theta right here. So now what we've done is, instead of our height, our angle at near point was going to be roughly the image height over 25 centimeters. Now our angle, the object height, now our angle is roughly the object height over the focal length. Okay, so we can stick into our definition for angular magnification. So theta is h over f. Theta near point is h over 25 centimeters. Cancel, cancel. And we end up with 25 centimeters over the focal length. So the shorter you make the focal length, the better. Now, there's only so far you can push this, and it turns out that it's really hard to make a simple magnifier that will give you a decent image with more than about 10x magnification. So to that end, if you're going to want to do more than that, you need to come up with some sort of a compound system. For instance, we could go and look at a microscope. So with a microscope, you're typically looking at a very teeny object. Say right here that you park in front of a objective lens, it's called. And again, you're going to stick it just outside the focal point. So the idea is that this is going to form a real image. Basically just inside a simple magnifier that we call the eyepiece. So then when you're looking at it over here, you wind up seeing, again, some absolutely huge virtual image. And as always with these devices, usually you like to park the image out at infinity. That way your ciliary muscles can stay nice and relaxed, and it reduces eye strain. Anyway, this distance here from the objective lens to the to the focal point of the eyepiece. This is the tube length L. In biological microscopes, that's a standardized thing. So this would be the focal length of the eyepiece. This would be the focal length of the objective here. So we can already see the images upside down. So our magnification is going to be the magnification of the objective times the magnification of the eyepiece, following a similar triangle argument similar to the one that we had just done. Sorry about that. It would give us a object magnification of the tube length over the focal length of the objective. And similarly for the eyepiece, that's our simple magnifier again, 25 centimeters over FE. And doing this, you can take things up to a couple hundred power before diffraction becomes a problem. Okay, that's great, you say, but what if the thing I want to see better is really far away? Well, then you make yourself a telescope. So again, same deal here. You're going to have a objective lens, and an eyepiece. And since with the telescope you're looking at things coming in from really far away, all the rays of light are going to be coming in parallel, and they're basically going to form an image pretty much right at the focal length. So we don't have to offer any ability to focus to form an image at the tube length or anything like that, like you have to with a microscope. So this is the focal length of the objective, that's the focal length of the eyepiece. And again, same kind of logic here, a pair of simple magnifiers. You can show that the angular magnification is equal to minus FO over FE, where FO is the focal length of the objective, FE is the focal length of the eyepiece. So here I want to raise a point, and that is that a lot of times people, they'll have some, a kid, in their family or whatever, or a friend, that they know that they've got this blossoming interest in science, and they'll go and buy them a telescope. And sadly, you go to the big discount stores, usually the thing you see marketed the most is the magnification of the telescope, and that's actually kind of sad. You can get yourself a huge magnification by just dropping in a very short focal length eyepiece. However, if the quality of the optics are poor, then you're not going to really be able to see much. Much more useful is to get a telescope that is large in diameter, preferably a mirror design for reasons we'll get into in a moment, because that will let in more light, and when we study wave optics, we'll see that it'll also allow us to have a sharper image. Okay, so what can go wrong with our optical systems? These are what we call aberrations. So we've already seen spherical aberration, at least touched on it a bit. So with spherical aberration, the issue is that the correct shape for either lens or a mirror turns out to be parabolic or sometimes hyperbolic, but either way, it's definitely not spherical. So this means that the rays won't all come to the same focus. So with both lenses and mirrors, the most straightforward way to fix this is to throw money at it to grind it to the correct shape. With mirrors, there's also, you could put a corrector plate in front, which is just a way of saying you're giving it some glasses to fix that. With lenses, there's a trick you can do, certain opticians can do, it's very trade secret, where they can continuously vary the recipe of glass across the diameter of the lens in order to get it all to come into the same focus. But we're getting better and better at grinding what are called aspherical elements. The selfie camera in your cell phone is a perfect example of this. It would be too hard to, it would take up too much space in your cell phone to put in the standard network of collection of lenses that you would need to undo all the aberrations. And so the solution is that instead of doing the usual design tricks, they actually just spend a little more money making the lens and grinding it to a non-spherical shape so that you get better focusing. Okay. A problem that is unique to lenses, and this is part of why I recommend that telescopes use mirrors, is chromatic aberration. We've already seen that blue bends better. So if I have a lens here, converging lens, if I have, let's say I've got a light source here, got rays coming to the principal, rays coming to the principal plane like so. Since we know that blue bends better, the blue light is going to come to a focus sooner than red light. Oops. There we go. With green light falling somewhere in between. So again, this happens in the human eye all the time, and basically the solution is to fix it in software. When we're designing optical systems, it would be best if we could avoid that altogether. So mirrors are a good choice. If you choose to use lenses, there is a trick where you can cement a converging lens of one index to a diverging lens of another index. By doing that, you can coax the red and the blue rays to come to the same focus. It won't be the same focus as the green, but the whole bundle will be a lot closer, and that will bring it to be smaller than a pixel on the CCD, which is good enough. Then finally, you can have coma. Coma can be due to a variety of things. For instance, you can have irregularities in the grinding, so quality control issues that cause not everything to come to a nice circular dot. Instead, it'll look kind of like a comet's tail, thus coma. You can also, and this is an issue with telescopes, and this is another reason why reflectors are more popular. So telescopes is, you often can wind up having an enormous objective lens. And if you point it up, it'll actually start to bend under its own weight a little bit and get misshapen. And if you point it out to look over the horizon, well, then it'll bend in a different way, so you can't get to have a consistent shape. And this is because you're supporting it on the edge. With a mirror, you can support it all around, and so you get a lot less sag. Well, at least until you build the big, huge ones that professional astronomers use. And then they use a technique called adaptive optics, where computers have actuators continuously vary the shape of the mirror in order to keep the shape perfect. Alrighty, I will catch you in the next one.